You ever wonder how we predict things that seem, well, completely unpredictable? I mean, think about it. The stock market, the weather, our world is just full of uncertainty. It feels kind of chaotic, totally random. But what if I told you there was a way to find some beautiful mathematical order in all that chaos? Well, that's exactly what we're diving into today.
And that's the big question, isn't it? If an outcome is totally up to chance, how on earth can we build a model or make a smart decision about it? I mean, just staring at randomness, that doesn't really give us anything to work with.
Well, here's the secret. The key is to find a way to convert those messy, real-world outcomes into something we can actually analyze. Cold, hard numbers. This is the bridge that takes us from chaos to clarity, and it sets the stage for the star of our show today. So how do we build that bridge? How do we do the translation? Well, let's meet the tool that makes it all possible, the random variable.
Okay, so here's the official textbook definition. It's a variable, right? But its value isn't just one fixed thing. Instead, its value depends on the outcome of some random process. And the most important word here is quantitative. It has to be a number. But honestly, a much better way to think about this is less like a variable and more like a translator. Yeah, that's it. It's a little machine that takes a random, real-world thing, like getting heads on a coin, and translates it into a numerical value that we can actually do math with. Let's make this super concrete with a classic example. Okay, step 1. Our random process is just flipping 2 coins. Simple enough. Step 2. We list out every single thing that could possibly happen. Statisticians call this the sample space. For us, it's getting 2 heads, a heads then a tails then a heads, or 2 tails. Now for the magic. Step 3. We define our rule. We're going to create a random variable. Let's call it x. And we'll decide that x is just going to be the number of heads we see. And poof, just like that, the translation happens. Heads heads becomes the number 2. Heads tails becomes 1. Tails tails becomes 0. See? We've just turned random coin flips into a clean set of numbers.
Awesome. Now that we know how to turn randomness into numbers, we need to know that these numbers basically come in 2 main flavors.
And the difference is actually really intuitive. It all boils down to one simple idea: counting versus measuring. On the left, you've got discrete random variables. These are things you can count, like the number of students who are absent. You can have 0 or 1 or 2, but you can't have 1.5 absent students, right? Then on the right, you have continuous random variables. These are things you measure. Think about the time it takes to run a race or someone's height. Those values can be anything within a range. It's a simple idea, but it's a really important distinction. Okay, so we've successfully translated random outcomes into numbers. But that's only half the story. The real power comes when we ask the next logical question. Okay, but how likely is each of these numbers? And that brings us to the blueprint for our random variable, its probability distribution. A probability distribution does exactly what it sounds like. It's basically a map that shows us the probability for every single possible value our random variable can be. For discrete variables, like our coin flip example, we often call this a probability mass function, or PMF for short. So let's go back to our coin flip. This table right here is its probability distribution. You can see the probability of getting 0 heads, which remember means getting 2 tails, is 0.25 or a 1 in 4 chance. The probability of getting exactly 1 head is 0.50 because 2 of our 4 possible outcomes gave us that value. And of course, the probability of getting 2 heads is 0.25 again. And if you're a visual person like me, this bar chart shows the exact same thing. It makes the distribution pop. You can see instantly that getting 1 head is the most likely outcome. In fact, it's twice as likely as getting 0 or 2 heads. This is what's so cool about a probability distribution. Now, these distributions aren't just random. They have to play by 2 really simple common sense rules. First, any single probability has to be a number between 0 and 1. You can't have a negative chance of something happening, and you can't have more than a 100% chance. Makes sense. Second, if you add up the probabilities of all the possible outcomes, they have to sum up to exactly 1, which just means, well, something has to happen. Okay, we've covered the what and the how, but now let's get to the most important part of all. Why does any of this actually matter? What's the point? You don't have to just take my word for it. This quote from a recent research journal pretty much says it all. These concepts, the probability mass functions for discrete variables and their cousin, probability density functions for continuous ones, they aren't just for a classroom. They are indispensable tools. And that's the real payoff.
Random variables are the foundation that lets us actually quantify uncertainty. They're what allow insurance companies to figure out your rates, engineers to design buildings that can withstand crazy weather, and those machine learning algorithms to suggest what you should watch next. They are the essential bridge from random chaos to smart, data-driven decisions.
So really, what this all comes down to is that random variables give us a language to talk about uncertainty. So I'll leave you with a question. What's a random process in your life? Maybe the number of red lights you hit on your way to work? How could you define a random variable to start making sense of it?